As no one else is in the meeting, so we'll wait uh, until someone joins, then we will start. Welcome, P. Hori Babu. Good evening. As you have joined, so we can start, I guess. I'll share my screen, and with your permission, I will record. And hopefully, I am loud and clear. I hope my screen is also visible. So let's start. Yeah. So good evening. My name is Shudru Sadhukan. I am a PMRF teaching assistant, and I am a PhD student at IIT Bombay. I am your facilitator for the live interactive session of week 9 of NPTEL course code AR18, which is Urban Utilities Planning, Water Supply, Sanitation and Drainage, offered by Dr. Devapratim Pandit, who is a professor of IIT Kharagpur at the Department of Architecture and Regional Planning. Where are we? We are at the ninth week of the month of September. Today is 22nd of September, and our session will start today with a very interesting problem. So we'll see the problem first. A table is given. At the left hand column of the table, there are time is written in hours. So from starting from 0 to the first hour, then first to second hour, like that way. 2 to 3, 3 to 4, In this way, the data of an entire day is covered. So in the left hand column, there are 24 hours. So the data of every hour is covered. And in the right hand column, the demand is given for that particular hour. Okay. And the unit of demand is ml. That is, it is not small ml, so it is capital ml. That means megaliters or million liters. That means this, for example, for the first hour, the demand is 0.1 ml. That means this many into 10 to the power 6. That means 10 to the power 5 liters is the demand for first hour. Then for the second hour, the demand is 0.2. That means 2 into 10 to the power 5 liters. That is the demand of the second hour. So and so forth. Welcome, uh, Khama Singh. So yeah, Hori Babu attended last class. I don't remember whether you attended the last class or not. So let's hope that you have watched all those lectures up to the week 8. The original lectures by Dr. Pandit and also the DA sessions, the tutorials ones. So if you have any doubt regarding any previous sessions, you can ask the questions, or otherwise we will continue. So we have just started with a problem where a table is given to you. Now you have to calculate the minimum storage volume required in order to supply the demand as shown in the table. If the inflow of water to the reservoir is maintained at uniform rate throughout the 24 hours using these data. So the demand data is given to you with the help of this table, right? Now the demand, you can see that for every 1 hour the demand is not constant, it is varying throughout the day. Let's say in the 8th hour, sorry, in the 7th hour, no, sorry, it is the 8th hour. So at the 8th hour the demand is 0.6 into 10 to the power 6, that means 6 into the power 5 liters. And at the 12th hour you can see that the demand is very less, it is 10 to the power 5 liters only. So the demand is basically varying. Now you have to design a reservoir. Basically you have to calculate the volume of the reservoir from where this supply, this water will be supplied to meet this demand, okay, throughout the 24 hours period. So based on this data you have to design the volume of the reservoir. You have to calculate what should be the volume of the reservoir, the minimum volume of the reservoir that you have to calculate. Okay, now here one data is given. If the inflow of water to the reservoir is maintained at uniform rate, that means if you remember one problem that we calculated in one of our earlier classes, it was a mixed tank problem where the flow is coming in and flow is going out. So at the steady state condition, the flow in will be equals to the flow out. But here you can see that it is not the steady state condition. So this volume of the reservoir within this, let's say this, let's assume this voluminous tank is situated at a certain height from where with the help of gravity the water is flowing out and it is being supplied to the town to meet this demand that is given in the table. But demand is varying, but inflow rate to the tank is not varying. It is mentioned, it is uniform, right, throughout the 24 hours. So you can see the flow in that will be equal to the flow out at the end of 24 hours. Okay, so whatever the demand will be there at the end of the 24 hours, the total demand divided by 24 hours, that will be your per hour flow rate. But in each and every hour, there will be fluctuations. So this tank will be designed basically to absorb the fluctuation, right? So you have to design the minimum volume of the storage tank such that it can absorb the fluctuation, maximum amount of fluctuation. You have to keep in mind the maximum amount of fluctuation in order to calculate the volume of the tank that they are asking. Okay, so keeping that in mind, we'll start solving the problem. So will you try this problem? Uh, can you respond? Will you try, or should I proceed with the solution? Because it will require let's say 10 or 20 minutes time for you to solve the problem. So should I wait for that, or should I proceed with the solution? Or you are not understanding the way how to calculate the volume in order to absorb the fluctuation? So whether you are able to understand or not, please respond. I'll wait for a couple of minutes. If you want to type, then you can type yes, no. What should we do? Should we proceed? Okay, I guess I should start solving the problem. So yeah, so let's start. First of all, the solution, detailed solution goes like this way. We have to first calculate the cumulative demand in, again, the same unit, that is the megaliters or million liters. So if the first hour's demand is zero point 0.1, then the cumulative demand of the first hour is 0.1. Then second hour's demand is 0 0.2. That means second hour's cumulative demand will be the first hour's demand plus second hour's demand. So 0.1 plus 0.2, that means 0.3. This will be the cumulative demand of the second hour. The third hour cumulative demand will be the cumulative demand of the second hour plus the demand at the third hour. Okay, so 0.3 plus 0.3, 0.6. In this way, it will proceed. So at the fourth hour, cumulative demand will be the demand at the fourth hour plus cumulative demand at the third hour. So whatever we have accumulated till now, that we have to take into account along with the demand of that particular hour to calculate the cumulative demand of that particular hour. So at the fourth hour, the cumulative demand will be like this way: 0.6 plus 0.3 equals to 0.9. In this way, 0.9 plus 0.2 equals to 1.1. That will be the cumulative demand of the fifth hour, so on and so forth. So in this way, let's say at the 22nd hour, the cumulative demand will be the cumulative demand of the 21st hour plus the demand of the 22nd hour, that means 6.25. For this 23rd hour, it will be 6.2 plus 0.1, 6.35. At the last hour, that is the 24th hour, the cumulative demand will be the cumulative demand of the 23rd hour plus the demand of the 24th hour, that means 6.45, and it is also the sum of the total demand because we are just adding like this way. Hopefully you are able to understand this. So first you have to calculate the cumulative demand, that is the total demand at the end of the 24 hour, which came out to be 6.45. So 6.45 is the total demand of the entire town or entire system for which you are going to design the tank per day. So it is the daily demand you have calculated like this way. Okay. Now let's proceed. So the explanation is total demand during the day will be the sum of all these values. So starting from 0.1 to 0.2 to 0.3 in this way up to 0.1. Okay. So we are just summing up the entire thing, and total demand during the day is coming out to be 6.45 megaliters or million liters. Okay, as we have calculated here also, right? Now is the total demand. Total supply during the day will be equals to total demand, because whatever the water that will be required by the town or the system, that amount of same amount of water you have to supply, assuming zero losses. So as in the problem they have not talked about anything regarding losses, so that's why we are calculating total supply equals to the total demand, which is nothing but again 6.45 million liters. Now, as in the question, they have told that the supply, though the demand is varying, but supply we are keeping it as constant. So total demand, total supply divided by 24 hours, that will be your hourly supply. So 6.45 by 24 equals to 0.27 ml megaliters. That will be your constant hourly supply rate. Hopefully it is clear till this point. If you have any problem regarding understanding, you can then and there ask. Now, next, we just put the value of the hourly pumping rate. So these two, 0.27 or 0.26875, this we have put here. So this is the hourly pumping rate in every hour. So if you sum up the entire thing or multiply the any one value with 24, it will come up to this value 6.45. So that the total supply is equals to the total demand. Okay. Now, next is we have calculated here the cumulative pumping rate. So these first two columns was given the cumulative demand that we just calculated. Then we just put the 6.45 divided by 20, the value we just put here, and then we are calculating the cumulative demand. Cumulative pumping rate or cumulative supply rate. So this is the just a shock absorber tank, you can assume, whose volume you have to calculate. Flow is coming in at a rate of 0.27 ml per hour, and flow is going out at this rate in different hours. Okay. Now total flow that came into the tank is 6.45, and the total flow that went out of the tank is again 6.45 at the end of the day. If you sum up all these total values, that means total demand equals total supply. So if you can design a tank which is having a volume of 6.45 ml, so you don't have to worry about the design conditions. This will be a huge large tank. Okay, so it will absorb all the daily fluctuations, so you don't have to worry about the uh, design of the volume in this case. But in the questions they have asked that the volume should be minimum, right? So that's why you have to consider the tank volume that will just absorb the fluctuation. So 6.45 will not be the answer. What will be the answer? We will see in due course. So now, after putting the value of the hourly pumping rate in megaliters, we are calculating here the cumulative pumping rate. Okay, that means similarly we have calculated here the cumulative demand, right? You have understood, I guess. Similarly, we have to calculate the cumulative demand for the pumping rate. So the first hour's pumping rate is 0.27 that we have put here. Second hour pumping rate will be 0.27 into 2. So this plus this, that will be second hour cumulative. Third hour cumulative will be this value plus this value, or 0.27 into 3, that will be the value of the third hour. Fourth hour demand will be 0.27 will be 4 into 4. Fifth hour demand will be sorry, not demand, fifth hour's pumping cumulative pumping rate will be 0.27 into 5, like this way. So at the end of 24 hours, it will be 0.27 into 24. That means 6.45. Here you cannot just multiply it with the number of hours. Why? Because the demand is not constant. So that's why you have to add up the previous hour's cumulative rate plus that hour's demand in order to calculate that particular hour's cumulative demand. But here you can directly multiply, and also you can add up with, similarly you can do in this table also. So because the hourly rate is constant here, but hourly demand is not constant. Supply is constant per hour, but demand is not constant. But whatever it is to constant or not, that doesn't matter, because at the end of the day you can see that it is coming out to be 6.45. So at the end of the day, the cumulative demand is equals to the cumulative pumping rate. So whatever the demand, that amount of pumping rate you have supplied here. Okay. So till this point, I hope it is clear. So now the next column we have added, it is the excess of supply. Okay, so daily supply is 6.45 ml, hourly supply is 0.27 ml, which is 6.45 divided by 24. Excess of supply, how we calculated that? We calculated this like this way. So we just subtracted the cumulative pumping in megaliters of that particular hour minus cumulative demand in megaliters of that particular hour. So let's say for the 14th hour, we calculated it like this way: 3.7625 minus 4.1. That came out to be minus 0.34. In this way, you can see we have calculated. So at the end of the 24 hour, you will see the value is 0 because the supply is matching exactly equals to the demand. So that's why 6.45 minus 6.45 came out to be 0. But you can see the fluctuations. This fluctuation is nothing but the difference between the demand and the supply. Basically supply minus demand. This is the value, excess of supply. The last column, 1, 2, 3, 4, 5, 6, the sixth column value is calculated like this way. You can see some value in this column are positive, some values are negative. So those negative values we have marked with red, and the positive values we have marked with green. Okay, so positive values means what? Positive values means supply is more than the demand. So the green columns up to the 7th hour, you can see here, up to the 7th hour, the demand is more than cumulative demand is more than the cumulative cumulative demand is less than the cumulative supply. But beyond the 7 hours, that is starting from the 8th hour, you can see that the excess supply is becoming negative. That means the demand is becoming more than the supply. So that's why you have marked this in red. Okay, clear so far? Now it is observed that maximum excess demand is 0.84 ml. So if you just observe the red colored data, you will see the maximum mod value or maximum negative value that we can get is at the 19th hour, that is 0.84 that we have calculated here. So the demand can go maximum of cumulative demand can go maximum up to these levels, or the difference between the cumulative demand and the cumulative supply can go maximum up to this level. And maximum excess supply, if you just look at the green marked data where the cumulative pumping is more than the cumulative demand, you will see the supply, the maximum difference between the pumping and the demand. That means the maximum excess supply can be 0.24, which is happening two times, one at second hour and another one at fifth hour. The value is 0.24 megaliters. Okay, so total storage that we have asked in the question, the volume of the total storage required will be maximum excess demand, that is 0.84 megaliters, plus maximum excess supply 0.24, which is nothing but equals to 1.08 million liters, which can be approximately equals to 1.1 megaliters. Okay, so why it is so? Why we are so this is the maximum fluctuation in demand and this is the maximum fluctuation in supply. So that's why we are adding them up in order to get the minimum storage volume required. So this will be the minimum volume of storage that will absorb these fluctuations. The other fluctuations like 0.17, 0.18, 0.08, this is the supply side fluctuations, and you can see the 0.31, 0.27, 0.5. All the other fluctuations are less than this 0.84 and 0.24. So that's why they can automatically be absorbed by the storage volume. So you can see that previously we were telling you can design a tank of 6.45 ml, but that will not be the minimum volume. So here, as we asked in the question, so it is far less than the 6.45. So far less capital investment will be required if we design the volume 1.08 based on this supply demand data, and also with this volume storage volume we can meet the requirement of the system. Okay, so now we'll see in a bit detailed manner why we have added them up in order to calculate the minimum storage volume. That we will see. So to observe that thing, we first this time column, you can see here the hours are written like 0 to 1, 1 to 2, 2 to 3, 3 to 4, 21 to 22, 22 to 23, 23 to 24. In this way, we have first estimated their midpoint, like point 0 to 1 we took the midpoint as 0.5. So yeah, so 1 to 2 we took this as 1.5. In this way, from 22 to 23 the midpoint will be 22.5. From 23 to 24 the midpoint will be 23.5. In this way we just modified the uh, time column. Okay, so it ran from 0.5 to 23.5. The demand is same as the previous, so it varies from 0.1 to 0.1. It is same, and these two these two columns, the hourly pumping rate and this column, uh, sorry, this thing we have kept constant. So yeah, so the hourly pumping rate we have kept as it is. So the cumulative demand and the cumulative pumping, these three columns. So column number 3 and column number 5. These two columns we have hidden. So only 1, 2, 4 and 6. So the modified chart is like this way. Now we have plotted a graph. So the graph is your demand or supply in megaliters or million liters versus time in hours. So it runs from 0 to 24 hours. You can see how the data is varying. So hourly pumping rate, the red marked or the orange marked line, you can see it is constant with time. Constant at what level? 0.27 ml per hour. So it is the rate is constant. Okay. You can see the blue line is the demand line. So demand line is varying around the supply. So if you calculate the area under the curve from 0 to 24 hours, the total demand will be equals to the total supply part. Okay, the area under the curve will be same. So though the demand is fluctuating, it is fluctuating around the supply curve. So the blue line and orange line, hopefully you are able to understand. Now this green line is the excess of supply. So the excess of supply is the difference between the cumulative supply and cumulative demand. So you can see the green line is moving around the y equals to 0 line. So this is the y equals to 0 line. This side is negative and the top side is positive. You can see that sometimes the green the demand was more than the supply was more than the demand. So that's why it was positive. So when the cumulative supply became less than the cumulative demand, then the difference became the negative. So at max, the negative value is coming at this level, which is at 18.5 hours. At 18.5 hours, between 15 and 20 hours, it is becoming the maximum negative, that is 0.84. And at 1.5 hours and 4.5 hours, the it is the above the zero line, so it is maximum positive, so 0.24. So this maximum positive value and this maximum negative value we are considering for the design of the tank. So the tank volume is basically starting from this level to this level. This is the tank volume. So 0.24 minus 0.84 to 0.24. This is the tank volume, or 1.08 or approximately 1.1 megaliters is the tank volume. Why you are considering that? So you can see that at the first hour, whatever the supply was there, whatever demand is there, this many amount of volume got accumulated. At the end of second hour, this many amount of volume got accumulated. So maximum the water level can go up to this level, 0.24, this level, this volumetric level. Otherwise it will be at the zero. Then at the negative side, that means whenever the supply, the pump is not supplying but demand is more, so the tank volume is becoming negative from optimal level, so it can go up to maximum 0.84 level. Then again recovery will start. So you can see the demand is less here, 0.3 to 0.1, demand is becoming less than the hourly pumping rate. So again the recovery phase will start, and some at the end of the day it will come at the steady state. So hopefully you are able to understand. So this many amount of volume, so 0.84 amount of water, 0.84 megaliters of water we have to maintain at the tank in order to meet the demand when the supply is less. And this many amount of 0.24, this many amount of excess volume we have to maintain in the tank whenever the supply is more than the demand, in order to accumulate the excess water to prevent the loss of the water. Hopefully you are able to understand. So there, this is the reason we are adding them up, the maximum negative value and maximum positive value, we are adding them up in order to get the answer, get the minimum storage volume that is required in our case. So this problem is clear. Now for those who will be watching the recording later, if you have any question, you can ask in the subsequent classes. Okay. Now we will move on to our next problem. Hopefully the last problem was clear. The next problem is a real estate project on a 12-hectare site contains 6 high-rise apartment buildings, each with a ground coverage of 3% of the site area and houses a residential population of 20,000. So there is a real estate project on a 12-hectare site. Okay. Within that area, there are 6 high-rise apartment buildings. each building has a ground coverage area of 3% of the site area. So 3% of 12 hectare will be area for one building. That means for 6 buildings, it will be 6 into that one. Okay, for one building, how many of area? That into 6. That will be the total area that will be covered by the building. And there are 20,000 people who are living in the 6 high-rise apartments. Now it is said in the problem that 20% of the site area is used for the gardens and or parks. So 6 into 3%, that means 18% area of 12 hectare is gone. Now how much is left? So 82% is left. Among these 82%, again 20% is gone and 62 is left. So this 20% of site area is for the landscape gardens and or parks. The rest of the area, that is your how many percentage is there? 62%, right? So 62% of the area is for roads and open parking. So there are three types of areas. One is the road area, AR you can assume. Another one is your building area, which you can assume as AB. And another one is for landscape area, you can assume as AL. So this 12 hectare is distributed among these three types of areas: landscape, roads, and buildings. Now, the site experiences an annual rainfall of 1,600 millimeters. You have to assume coefficient of runoffs for landscape area and roads or paved area to be 0.15 and 0.65 respectively. So coefficient of runoff is almost nil in case of building area, but it is 0.15 in case of landscape area and 0.65 in case of road or paved area. Can you say that why the coefficient of runoff is more in case of roads or paved area as compared to the landscape area? So why the coefficient of runoff is less in case of landscape area? Can you say? To comment on that. So based on whatever data is given till now, you have to calculate the average surface runoff from the site after a heavy rainfall of 150 millimeter within the 2 hours. Okay, so for 2 hours you have to take 150 millimeter. That means total 300 millimeters of rainfall has occurred. For that amount of rainfall, you have to calculate the total surface runoff. So total surface runoff will be from the landscape area and the road area, but there will be zero surface runoff from the building area, as the coefficient is not given. Coefficient of runoff is not given for the building area. Okay, so this 18% area will not contribute towards the surface runoff. Why it is so? Why the coefficient of runoff is more in case of road as compared to the landscape area? Can you say? Okay, so the reason is basically the you can see the in case of roads or paved area, the ground is cemented, but in case of cemented or by coulter or whatever means, it is ground. The ground is basically artificially covered. But in case of landscape area for garden and all, the ground is not covered. So the amount of rainfall that will occur in case of landscape, most of it will get percolated inside the soil because the land is not cemented. So runoff will be less. So runoff coefficient will be less, 0.15. But in case of road or paved area, the uh, rainfall that will occur in this case, that will not be able to easily go into the groundwater recharge. So most of the most of the amount of the rainfall will be runoff in case of paved area. So that means the AR, that is the road area, it will mostly contribute into the runoff. So that's why its runoff coefficient is more as compared to the landscape area. Okay, so I will wait for a couple of minutes for you to solve the problem. Then I will return back and again to tell you the answer. Try it in your copy and type the answer in the chat box. What will be the total runoff that will get generated for the 2 hours of rainfall for 150 millimeter per hour? Okay, so let's find out. I'll wait for a couple of minutes. Not able to solve? Read the problem again. Okay, we'll solve the problem. So the solution is building area AB will be, so 12 hectare is the total area, 0.03% is the building area for individual building, and there are 6 high-rise buildings. So it will be 6 into 0.03 into 12. So 0.18 into 12 is 2.16 hectares. So the building area AB can be written like this way: total area minus landscape area plus road area. Okay. Now landscape area, which is this AL, that is 20% of the total area, that is 12 hectares. That means 2.4 hectares. And this landscape area AL again can be written as total area minus under bracket building area plus road area. Okay. Now next is area for roads or open parking will be this total area 12 hectares minus the sum of these two areas. That is 2.16 plus 2.4, which is equals to 7.44 hectares. This road area, that is AR, can be written as AG minus AL. So this AG is the ground area. This AL plus AR, the summation of between these two, it can be written as AG or ground area, because building area is separate. So AL plus AR means AG. So if you subtract this AL from the AG, it will give you the AR or the road area. Okay. Now, rate of rainfall or I millimeter per hour will be sorry, there was one mistake in the while studying the reading the problem. So heavy rainfall of 150 millimeter is within these 2 hours. So it is not per hour. Okay, that means per hour rainfall will be 150 divided by 2. That is 75 millimeter per hour. Welcome, Sureka. We have only solved one problem, and second problem we are just solving. So the previous problem you can watch in the recording. Okay. So per hour rainfall will be 75 millimeter per hour. Now, surface runoff formula will be Qg equals to Ci into Ag by 360, where this C is runoff coefficient. So CIA by 360. It is the formula for the runoff. How this formula came into the picture, that we will explain. So C is the coefficient of runoff. See, coefficient means what? The fraction of the total rainfall that is contributing to runoff. That is the coefficient of runoff. I means the rainfall, A means the area. So rainfall is given in millimeter, that is the unit of length. If you are multiply it with area, it will give you the volume. Surface runoff you have to calculate in volumetric unit. So it is giving you the volume. C is unitless fraction. So CIA you can understand. Why this 360 came into the picture? So you can see the I is given in millimeter. Area is given in hectares. So 1 hectare you have to convert it into meter square, and this I millimeter you have to convert into uh, meter. So if you convert these hectares into meter square and millimeter into meter, after conversion it will give you a factor of 10, and divided by 3600 will be there, because 1 hour 24 hour means 1 hour means 360 seconds. So 3600 divided by the 10 of the numerator came in the denominator, giving you this factor 360. Okay, so this is nothing but originated due to the unit conversion from hour to second, from hectare to meter square, and from millimeter to meter. This factor came into the picture for that reason. Now, for the landscape area, the runoffs will be QL, which is nothing but equals to this CIA divided by 360, this same formula. So for the landscape area, it will be the coefficient of runoff for the landscape, that will be, that is as it is given in the question as 0.15. I will be your rainfall, so 75 into 2.4, it is the area that you have calculated for the landscape. So it is AL, okay, which is nothing but equals to 0.075 meter cube per second. Similarly, for the roads, that is the paved area, runoff will be QR equals to the coefficient for the road, which is more than the landscape. Why it is so, I have explained. 0.65 into 75. The rainfall is same, there is no difference, into area is different again. The road area that we earlier have calculated, AR equals to 7.44 hectares divided by 360, which came out to be 1.0075 meter cube per second. So this is the landscape area, this is the road runoff. Now building will not contribute to the runoff. That's why total runoff QG will be equals to QL plus QR, which is nothing but equals to 0.075 plus 1.075 meter cube per second, which is nothing but equals to 1.0825 meter cube per second, approximately 1.1 meter cube per second. Hopefully you are able to understand. Many people have joined. Welcome Aruna and Dipti. So it is the second problem we are solving today. You can watch whatever we have discussed in the recording that will be uploaded in the YouTube. As you have joined late, so we will not take any break. We will just continue. Okay. Uh, so this problem is clear, hopefully. Now we will solve a MSQ, which is a multiple select question. It will be. So which one of the or more than one of the following factors do or does not contribute as explanatory variables for the predictions of temporal variations in water demand? Option P is built-up area, option Q temperature, option R is housing topology, and option S is wind speed. So more than one option may or may not be correct. You have to type the correct option in the chat box. Okay. So I'll wait for a couple of minutes. Yeah, anyone? Okay, I'll proceed with the solution. So the build-up area and the housing topology, the option P and R, these are the two options that they do not contribute as explanatory variables for prediction of the temporal variations in water demand. Here is the explanation. So build-up area and education are exploratory variables for predicting spatial water demands, whereas temperature and income contribute to the explanatory variables for predicting temporal water demands. Okay. So build-up area and housing topology, these two are the exploratory variables, and temperature and wind speed, these two are the explanatory variables. So that's why they don't contribute. It is clear. Now we'll proceed to our next MSQ. Again, a multiple select question. So which one of the following factors or more than one of the following factors affect the volume of the storm water? Option A soil wetness, option B land usage, option C land cover, and option D is percolation. Again, I'll wait for a couple of minutes. Type your answer in the chat box. On. Okay, I'll proceed with the solution. So all are the correct options. Okay, all of the factors, soil wetness, land usage, land cover and percolations affect the volume of the storm. Why it is so? Hopefully it is clear to you. So if the soil wetness is more, it will stormwater will be more. How you are using the land, because stormwater is nothing but the surface runoffs. So how you are using the land, that will contribute to the land water, sorry, stormwater. Okay, paved area will contribute to more. Land cover, again unpaved area will contribute to less amount of stormwater. And percolation, if more amount of water is getting percolated into groundwater recharge, then the volume of the stormwater will be less. So all the factors contribute for the for affecting the volume of the storm. Now, next there is the problem where you have to calculate the minimum number of dispersion trenches to be provided in an area if the area required for single dispersion trench is 70 meters square. Okay, there is one hint. You have to consider the width of the dispersion trench as 1 meter. Okay. So if you have watched the lecture of Dr. Devapradeep Pandit, then you will be able to understand. You will be able to answer. I'll wait for a couple of minutes. Please try this one and type your answer in the chat box. You have to calculate the minimum number of dispersion trenches that is to be provided if the area required for single trench is 70 meters square and width of the dispersion trench, one dispersion trench is 1 meter, that is okay. So basically you have to calculate the total area and you have to divide the total area with single dispersion trench area 70 meters square. That will give you the number of dispersion trenches. That's all. Okay. So there is on memory data, memory based data that you have to remember here. So I'll proceed with the solution if you don't remember. So maximum universal length of any dispersion trench is 30 meter. So it is given. Given means you have to remember this. So maximum, if you want to calculate the minimum number of dispersion trench, then you have to take the maximum length, right? If you minimize the length, then the number will increase. So as you are calculating here the minimum number of area, so maximum universal length of any dispersion trench that you have to consider here. So it was told by Dr. Pandit in his lecture. So it is 30 meter. So now it is pretty easy. Now you should be able to calculate. There is nothing in the problem now. Okay, so if you're not able to answer, I'll proceed. So total length will be total area divided by width given. Okay. So area required for single trench is given as 70 meters square, that we have put here area, and width given, it is also given in the hint as 1 meter. So in this way we can calculate the total length of one dispersion trench, which is 70 meter at maximum. So yeah, no, not maximum. So it is as it is given in the question. So 70 meters square is the area and 1 meter is the width. So length will be 70. So you can calculate the other ways also. So this 30 meter you can multiply with 1 meter and you can get the area as 30 meters square, and again you can divide 70 with 30, it will give you the same answer. So you can calculate the length, and lengthwise also you can calculate. So now the solution will be number of trenches will be equals to the total length, which is 70 meter you have calculated, divided by maximum length, that is 30 meter. Okay, which gives you 2.333. So number cannot be a fraction, as the length cannot exceed 30 meter, but you have to cover the entire area. So if you take two number of trenches, then it will cover 30 into 260 meters, and 10 meters square area will be left without covering, which is not acceptable. You have to cover the entire area. So you cannot increase this length, but you can minimize this length and you can increase the numbers. So that's why the minimum number will be 3. So if you take the 3 minimum number of trenches, so the area will be 70 divided by 3, which is a bit less than this 30 meter, which is acceptable because 30 meter is the maximum length. Okay. So as the length cannot exceed 30 meter, minimum 3 trenches is to be provided. Hope it is clear. Now we will move on to our next MCQ. So which one among the following statements is correct? Do you want to say something? Okay, you just joined. That's why. Okay, no issues. Option A is greater the intensity of rainfalls, the higher are the durations. Option B is high intensity storms usually have higher frequencies. Option C, greater the intensity of rainfalls, the lower are the durations. And option D is intensity of rainfalls cannot be predicted. I just showed you the answer. Okay, no issues. So here they are just asking the relation between the intensity of the rainfall and the duration of the rainfall. As you can see, the amount of water cloud can hold is finite in nature. That's right. So if the frequency of the rains are more, that means rains are happening more frequently, then the intensity of each rainfall will be less. But the intensity, if the intensity of each rainfall is more, that means all the amount of water is falling down in a single or two rainfalls. So then the frequency will be less. So that's why it is natural that they should be inversely proportional, right? The relation should be inversely proportional. That means the answer is the C. Greater the intensity of the rainfall, the lower are the durations. The explanation is as follows. So greater the intensity, lower is the duration. High intensity storm usually has lower frequency. Both frequency and or intensity of the rainfalls can be predicted like this way, because the total number will be finite. You can assume that the multiplication of the number of rainfall that is occurring or the frequency into the number of the amount of rainfall, average amount of rainfall you can assume per session of rainfall, which is equals to constant. So that means they are inversely proportional. If one is more, another one will be less. Now, next MCQ. The minimum consumption of domestic water in LPCD unit is option A 100, option B 115, option C 120, option D is 135. LPCD means liter per capita per day. That means liter per day used by a single person. Liter per head per day, that you can also consider. So one single person in a single day is using how much liter of water? What is the domestic standard of that? That value you have to say 100, 115, 120 or 135. If you remember from SAR's lecture, then you will be able to answer. It's a memory based question. Otherwise, you'll wait for a couple of minutes before moving on to the solution. And type in the chat box. No one has answered till now today. Please type. Okay, so if you nobody is able to answer, what is the solution? One. Okay, so the answer is 135. 135 LPCD is the minimum consumption standard for domestic water. Okay. Now, next MCQ is the water storability or the ability to store water of water bearing strata depends on option A porosity, option B particle size, option C both porosity and particle size, option D is none of them. The ability of water bearing stratum to store water depends on which factor, porosity or particle size, or both or none. I'll wait for 1 minute. Okay, so let's move on. So answer is both A and B. Explanation is porosity is defined as the percentage of voids present in a given volume of soil and or aggregates. Hence, ability of water bearing stratum to store water depends on both the porosities and size of the particles. It is the definition itself that is giving you the answer. The definition of porosity, hopefully you are able to understand. So if there is a volume of, let's say you have taken a beaker and you have put a sand inside the beaker up to the brink, up to the neck level. Then you just pouring water into the pot. So you'll see it will get filled up, but the sand will not overflow at the beginning. So there will be pores inside the sand. That means vacant spaces within that volume. Though the volume is looking full, but still there is vacancy that water can go into. Our memory is like that way. So we think that our brain is full, we cannot take further. But yes, there is the capacity is basically a relative term. You can always uh, gain more and more knowledge. So one saying was there. So there's our brain is a layer of different cells, right? If we take a single layer, a single celled layer, and we just spread our brain like a blanket or like a bed sheet, it will cover the entire map of India. like that. So it has so much capacity in a single space to store the memory. Okay, so porosity is like that way. Is the volume, because if you see the atoms and molecules, you will see most of the spaces of the atoms and molecules are basically vacant. The entire mass is stored in the nucleus. Okay, so that's why. In this case also, the water bearing capacity is dependent on both the factors, that is porosity and the particle size. Now we'll move on to our next MCQ. How much LPCT is required for the institutional or commercial purposes in a highly commercialized city? You have to fill in the blank. Option A is 80, option B is 100, option C is 50, option D is 30. Type in the chat box. I'll wait for 1 minute. LPCT means liter per capita per day. How much amount of water in LPCT unit in a highly commercialized city is required for institutional or commercial purposes? Type in the chat box. Nobody is typing today. Okay. Okay, Surekha has told us 50. So no issues. The answer is 50. You have told it correctly. If others are not able to answer, then also no issues, because this is just a memory based question, no concept in. Okay, so we'll move on to our next question. It's an MCQ. What is partial area effect? There are four options. One is greater than, another one is less than equals to, another one is less than, another one is equals to. So there are terminologies, those are used in these relations. We have assumed runoff coefficient equals to capital R, full catchment area equals to FCA, lesser catchment area equals to LCA, and higher rainfall intensity equals to IH, and lower rainfall intensity equals to IA. This we have assumed. So the relations are like this way. Previous question Surekha was right. So these are like this way. So R into LCA into IH is greater than R into FCA into IL. R into LCA into IH is less than equals to R into FCL into IL. R into LCA into IH is less than R into FCA into IL, and R into LCA into IH is equals to R into FCA into IL. So all the left hand terminologies are at lower TC, and all the right hand terminologies are higher TC. This is the critical temperature. The full catchment area is FC and less catchment area is LCA. So all the right hand terminologies are FCA, left hand terminologies are LCA. Runoff coefficient into the rainfall rate into the catchment area. So this is basically the CIA that we saw in the problem. Lower catchment area into higher rainfall intensity, and in the right hand side it is given as the full catchment area into lower rainfall intensity. And coefficient is same in this case. The coefficient you can just forget about the coefficient. You can just focus on this term. So LCA into IH and FCA into IL. So whether this lower area into higher rainfall, higher area into lower rainfall, whether they are equal or one is greater than the other. That is the question. So the relation is what called as partial area effect, whether it is greater or equal or less. So whatever be the correct relation, that correct relation is defined as the partial area effect. So you can see there is full catchment area and there is lesser catchment area. That means FCI equals to LCA. That means that's why it is written like this way. Yeah. Okay, we'll move on to the solution. So the answer is option A. Lower catchment area into higher rainfall is greater than the full catchment area into lower rainfall intensity. Okay. So rainfall, you can see at lower TC has is affecting the term more as compared to the lower rainfall in higher TC. So though there is lower area in the left hand side and higher area in the right hand side, that right hand terminology is less than the left hand terminology. So rainfall has more effect than the area in determining the relation between the two. Area has lesser effect than the rainfall. So rainfall is more important than the area where it is falling under the partial area effect. The area that is less important than the both are important, but area is less important as compared to the rainfall that is occurring. That's why we have ended up in this relation. Now our next is column matching. So you have to match the following LHC term or left hand column terminologies with their right hand column definition. So in the left hand column there are terminologies, in right hand column there are definitions. The terminologies are PQRS, so porosity, groundwater yield, hydraulic gradients, and artesian wells. The definition is given in the right hand column. So you have to match with their proper definitions. This left hand column PQRS, you can keep it as same and tell me the correct order of the right hand side. The first is the differences between the levels of potentiometric surface at any 2 points divided by the horizontal distance between them. Number two is wells from which water flows automatically under pressure. Number three is the quantity of water extracted by gravity drainage from a saturated water bearing stratum. And option four is the percentage of voids present in a given volume of soil or aggregates. This is quite easy. So all of the options you may not identify them correctly. So you can see there is artesian wells. As the term well, where is it in among these options? So you can see the second option carries the term well. So this S should be linked with number two, right? Artesian wells are wells from which water flows automatically under pressure. We have also seen different types of artesian wells in our previous classes. We have also seen the picture of artesian wells, the real life picture, how it is frozen, how it gets frozen in winter. We have defined it multiple times. In this class, we have solved problem on porosity. So you should identify the definition of the porosity among these options. The percentage of voids present in a given volume of soil or aggregates. The void that is present in a particular volume is defined as the porosity. So P is linked with 4, S is linked with 2, P is linked with 4. So it will start with 4, end with 2. So only 1 or 3 are left for these two things, Q and R. These two you have to identify and tell me the correct answer. Please type the correct order. You will start with 4 and end with 2. Only 1 and 3 you have to identify. Which one is correct? I'll wait for a couple of minutes. Type it in the chat box. Q is related with 3. The quantity of extracted water pressure, gravity. Okay. So saturated water bearing stratum will contain a certain amount of water, but entire amount of water you cannot you can extract with the help of gravity drainage only a certain amount of water. So if there is a fraction involved, so there is a total amount and you are determining the ratio or the fraction from the total amount. So the ratio of the certain amount by total amount, that basically gives you the yield, right? So Sureka has identified it correctly. So Q is 3, that means only one is left. Hydraulic gradient R is linked with the option 1, that is the difference between the levels of potentiometric surface at any 2 points divided by the horizontal distance between them. So 4, 3, 1 and 2 is the correct order. Yeah. Now I'll move on to our next MC. So Darcy-Weisbach formula for determining the head loss due to friction along a given length of pipe to the average velocity of the incompressible fluid flow is option A, option B, C and D. There are 4 relations are given. In the last class, we solved a problem based on the Darcy's equation. So there you have to determine the power of the pump, how much power one pump will put for fluid flow, that determines your the volumetric flow rate of the fluid that you want to achieve and the head that you want to achieve. So Q into H will be equal to the power of the pump that multiplied with certain factors. If you are considering horsepower, then you have to take into account the conversion factor from watts to horsepower. That means 1 watt equals 746 watts. That you have to consider. Again, the G you have to consider. G is what? G is the gravitational acceleration. So G into Q into H. That is your power formula. So Q is dependent on the, if it is a heat exchanger, then the amount of flow rate of water will be determined with the help of the MCP delta T. But that is not our concern here. Here our concern is the H, that is the pressure drop. Mostly, if there is no bend, only straight line, and you are supplying the water to a certain distance, there is length is involved, then Darcy-Weisbach equation is the formula with which you calculate the pressure. Okay, so as the fluid is flowing, there is inner surface of the pipe, and the fluid is there is friction between the inner surface of the pipe and the outermost layer of the fluid that is flowing through the pipe. Due to that friction, the pressure drop is occurring. To mitigate the pressure drop, you have to impart power in the pump. This type of problem we solved in our earlier classes, where we saw the Darcy-Weisbach formula. So to determine the Darcy-Weisbach formula, you had to keep in mind one thing. So there are 2 types of friction factors. One is Fanning's friction factor and another one is Darcy's friction factor. So Darcy's friction factor is denoted as FD and Fanning's friction factor is denoted as F suffix small f or only small f. So F Darcy FD or Darcy's friction factor equals to 4 times of the Fanning's friction factor. Fanning's friction factor is smaller than the Darcy's friction factor. So that actually is incorporated in the pressure drop formula that is given here in this question. So H is the pressure drop, but that is divided with the gravitational acceleration. So that's why the unit of H is in meters. You can see all the terminologies in the right hand side. There is G. So if this G if you take this in the left hand side, it will be meter square per second square into, if you multiply it with rho, that is the density of the water, it will give you the pressure. It will come in under the pressure. So H rho G, that will give you the unit of pressure. Okay. So yeah, please tell me the correct formula of Darcy-Weisbach equation. Only the factors you have to look. LV square. So this all are LV square by GT, right? This one only is LVQ. So option C is not correct, because if you do the dimensional analysis, you will see the L into VQ, it is not matching with the left hand side. It must be meters, right? Right hand side, if you see, V is the velocity unit. So meter cube per second cube into, so it comes out to be meter to the 4 divided by G, it means meter per second square, and D is in meter. So meter square per second square, it is coming as meter square, not in meter. So option C rules out. Only the 3 options are left. So the first factor is 2 by 3, second factor is 1 by 4, and fourth factor is 1 by 2. Which factor is correct? A, B, or D? That you have to. Sureka is telling us option D. Now we will see the answer. So hint is, as I told you earlier, Darcy's friction factor is FD, Fanning's friction factor is small f. Relation between these two is FD equals to 4f. And Sureka has identified it correctly. Option D is the correct answer. So if you put this FD as 4f, it will come out to be 4f LV square divided by 2GD equals to 2FLV square by GD. In this way, you can remember. Either you can remember the Fanning's friction factor formula, or you can remember the Darcy-Weisbach. Anyone you can remember, and you can remember this relation FD equals to 4f. In this way, you can remember the other formula, whichever you like. Okay. Now we'll move on to our next problem, which is basically a fire demand problem. Here you have to estimate the total fire demand for a small city with a population of 50,000 if two fire breaks out in a day and each fire lasts for 2 hours. So there is 2 fires and each fire lasts for 2 hours. So total 4 hours of fire. Now the discharge required for fighting each fire is given as 1 kiloliter per minute. So for 2 fires, it will be 2 kiloliters per minute into 2 hours. So hour you have to convert into minute, or minute you have to convert into hour, whichever you like, because unit is not asked here. Okay, you can calculate the fire demand in any unit. I'll wait for 3 minutes for this problem. All of you should calculate this and type the answer in the chat box. You can take per capita demand also, or you can take give me the total demand, whichever you like. So if you are calculating the per capita demand, then you have to divide the total demand by 50,000. Otherwise, if you don't consider this data, the population data, then only the total demand without per capita will be the answer. Whichever you like, but all of you should calculate this. This is very easy. I'll wait for 3 minutes for this problem. Couple of minutes more. One minute more. No, only Surekha has given the answer for the last three questions. P. Horibabu and Deepti Rani should also try, and Aruna also. Okay, we will proceed with the solution. So the solution is simple. Amount of required water is basically your the fire demand, which is nothing but equals to number of fires into rate of discharge into time divided by population number if you are considering it per capita. The number of fires is given in the question as 2. Rate of discharge is given in the question as 1 kiloliter per minute. So this we have converted into 1 kiloliter means 1000 liter, and per minute we have kept it as same. This 2 hour data, this time equals to 2 hours because each fire lasts for 2 hours. That you have converted into minutes. So 2 hours into 60 minutes. That gives you the unit in liters divided by 50,000 people. That gives you the liters per capita. So it is 2000 divided by 120. That means sorry, into 120, which gives you 4000 into 60. That means 24,000 divided by 50,000, right? That means 24 by 50 or 48 by 100. Sorry, 480 by 100. Yeah. So it gives you, yes, 4.8 LPCD, or if you are not considering per capita, that means 4.8 into 50,000 liters per day, 4.8 into 50,000 divided by 1000 kiloliters per day, or 240 KLPD. This is the answer if you are not considering per capita, or LPCD if you are considering per 4.8 LPCD or 240 KLPD. If any one of these two you have got, it will be correct answer. Yes, Hori Babu, go ahead. What do you want to say? Okay, nothing. Surekha, maybe some calculation mistakes may be there. Otherwise, hopefully this only you have done. I mean, the way of solving the problem is same, right? Or you have applied some different method. Okay. So hopefully you are able to understand. So now, but yes, as you have tried, it is highly appreciated. You have given answer all the previous questions as correctly. So I have multiple times told you all that you don't have to be shy away. This is just a practice session. It is not. It will not be evaluated. So now our next is one MSQ. So multiple set question. More than one option may or may not be correct. Design of the pumping station for the drainage of storm water directly depends on pumping points, quality of sewage. Option C is estimation of design runoff at the pumping station. Option D is capacity of the waterway and additional storage capacity. So more than option may be correct. You have to identify the correct option. I'll wait for a couple of minutes. Dipti, Aruna, Horibabu and okay, Dipti, Aruna and Horibabu, you three try. Pumping station design for the drainage of storm water directly depends on which of the following factors. One is pumping points, another one is quality of sewage, another one is estimation of design runoff at the pumping station, and capacity of wet oil and storage capacity. Basically, it is your additional plus storage, total capacity of the wet oil you can consider. The capacity is basically nothing but the retention time in minutes for peak load. So if there is a peak load and you know the retention time, if you just multiply these two, you will get the capacity of the wet oil. Plus additional storage capacity, it is just a design relaxation you have to consider. Then the total capacity. So the total capacity, pumping points, quality of sewage, and the estimation of the design runoffs at the pumping station. Which of the following factors are considered while designing the pumping station for the drainage of storm? Only Surekha is trying. None of you else are trying. So others should also try. Surekha, you can also try. Yeah, Surekha is telling us option D. Okay, we'll move on towards the solution. So option D is correct option, but also option A and C are correct because it is a multiple choice question. Quality of multiple choice question. Quality of sewage, it is not considered while designing pumping station for the drainage of storm water because storm water has nothing to do with the sewage. If it was designed for sewage treatment plan or STP, then you have to consider the quality of sewage also. But as it is not there, so only the pumping points, the estimation of design runoff for the pumping station, and the total capacity of the wet oil, these three are considered. Okay? The quality of sewage is not considered. It is clear. Now we'll move on to our next MC. So among the following statements, the incorrect statement is option A, infiltration is inversely proportional to the porosity of the soil. Option B, at a slow rate of rainfall, more quantity percolates to the ground and lesser amount goes into the runoffs. Option C, specific yield is the ratio between the volume of water obtained by gravity drainage to the total volume of the subsoil strata. And option D is sand and gravel are important aquifers for public water supplies. So you have to identify the incorrect statement. So let's look at the option B. At a slow rate of rainfall, quantity percolates to the ground and lesser amount goes into the ground. That is he saying. Yes, definitely. Because you can see the again Horibabu want to say something? I don't think so. I lower your hand. If you want to say something, you can unmute yourself and speak. Okay. So if you see the rainfall rate is slow, then definitely runoff will be less. But uh, I mean, as less amount of water is going to the runoff and more amount of water is staying because of the slow rainfall, more quantity will percolate to the ground because the percolation needs the mass transfer through the voids or through the pores of the ground. So option B, I think, I guess it is correct because it is not an MSQ. One option only will be incorrect. Right? If you see the option D, sand and gravel are important aquifers for public water supplies. I think it is also correct. Important aquifers for public water supplies. Yeah, because sands and gravels are used in case of sand filters or gravel filters, and also where the aquifer, I mean the artesian wells are used for public water supply, then through the sand and gravel layer, the water can percolate easily. So option D should also be correct. So it should be either option A or C, which is not correct. Which one will be? I don't know if you have tried it or not. So yeah, we'll see the again Horibabu. So option A is not correct. Infiltration is inversely proportional to the porosity of the soil. It should not be correct because uh, if there is more porosity, the infiltration or the percolation will be more. So it should be directly proportional, not inversely proportional, right? A specific yield, the definition is given correctly. So specific yield is the ratio of the volume of water obtained by gravity drainage to the total volume of the subsoil stratum that we just saw it in one of the earlier problems. Maybe it was a column matching where we saw, right? So it is also correct. So the explanation is as follows. Infiltration is directly proportional to the porosity. When the surface is more porous, it can hold more water and hence increases the infiltration. More porosity means more void area to hold the water. So if the porosity is more, it will increase the infiltration. That's why it is not inversely proportional, it is directly proportional. Option A is incorrect. Now we'll move on to our next MCQ. Calculate the maximum hourly conversion in LPC based on the average daily consumption of 280 LPCT. Option A is 18, option B is 17.5, option C is 17, option D is 18.5. LPC means liter per capita. So average daily consumption is given as liter per capita per day. Hourly conversion will be how much? So liters per capita you have to calculate, right? So average daily consumption is given. If you want to calculate the average hourly consumption, then you just have to divide the average daily consumption with 24 hours. So 280 divided by 24 hours, it will be your average hourly consumption in LPC. So what will be the relation between the maximum hourly consumption and the average hourly consumption? That you have to remember. You have to recall from the lecture. What is the relation between the maximum and the average? If you recall, then you just have to multiply the 280 divided by 224, this factor with your recalled factor. So just the multiplication will be the answer. I'll wait for a couple of minutes. Please try to solve. Option B is where I study. Okay, solution. I hope you are correct. So let's see. So the answer is option B. Yes. So you remember the factor, I guess. Very good. Now the explanation is maximum demand equals to 1.5 times of the average consumption, which is nothing but equals to 1.5 into 280 LPCD equals to 420 LPCD. Now from the daily consumption, we have to convert it to hourly consumption. So maximum hourly consumption will be equals to 420 LPCD divided by 24 hours per day, which is nothing but equals to 17.5. Very good. Okay. So the relation is between the maximum and average is maximum is 1.5 times of the average. That only you have to remember. Okay. Now I'll move on to our next multiple select question. The major problems plaguing groundwater management in India is are choose the correct answers. Option A, no proper registering of wells. B, no rules on user rights and metering. Option C is pollution in the form of industrial pollutants, human wastes, and or agricultural chemicals. Option D is frequent breakdowns of pumps in wastewater treatment plants. So, which one, more than one, maybe may also be correct. So, which problems are plaguing the groundwater management in India? Which of the following problems? No proper registry of the well, no user right and metering, uh, pollution from agricultural waste, industrial pollutants or human waste, and so no proper registry, no metering, pollution, and another is breakdown of pumps in the wastewater. Horibabu has answered option D. You have to choose the correct answers. It is the multiple select question. Okay, I'll tell you the answer. D is the opposite. So D is not the correct. All the other factors are basically correct. All the others are the major problems. Those are plaguing groundwater management in India. The frequent breakdown of pumps in wastewater treatment plants, it has nothing to do with the plaguing of groundwater management. Okay. Yes, option C is correct, and option A and B are also correct. This is an MSQ. Option D is not correct. Okay. We will move on to our next MCQ. It is multiple choice question. One option will be correct. Considering breakdowns, water treatment plants pumps are designed for how many times of the average water consumption? Fill in the blanks. Option A is 2, option B is 1.5, option C is 2.7, option D is 2.5. In the last problem, we saw that the consumption, if you are considering the consumption or the demand, then the relation between the maximum and the average is 1.5, 1.5 times. Okay. But when you are not considering that consumption, you are considering here the breakdown of pumps. Okay. Then how many times you have to consider with respect to the average water consumption? That you have to answer. Here it will not be 1.5. So I am giving you an hint. So option B will not be the answer. Either option A, C, or D will be the answer. So Horibabu is telling us 2.7. Option C. We'll see the correct answer. So option A, 2 is the correct answer. Okay. So just again recall, whenever there is demand or consumption, then the maximum demand will be 1.5 times of the average consumption. Whenever you are designing pumps for water treatment plant, for you are considering the breakdown, then you have to take 2 times for the design purpose with respect to the average consumption. So the design capacity will be 2 times of the average water consumption whenever you are considering the breakdown. But in case of consumption, the maximum will be to 1.5 times of the average water consumption. So average water consumption into 1.5 times, average water consumption into 2 times. 1.5 times when you are considering maximum consumption, 2 times whenever you are considering breakdowns. Okay. Now next MCQ, multiple choice question. Which one of the following isn't an example of on-site sanitation system? Option A is port flush water seal latrine. Option B is septic tank. Option C is leach pit. Option D is pressure sewer. Which one of the following is not an example of on-site sanitation system? Okay. So the answer is pressure sewer. All are things: septic tank, leach pit, and your port flush water seal latrine. These all of the three are on-site sanitation systems examples. Only the pressure sewer is not a on-site sanitation system. These are memory-based questions. So if you are not able to answer or you are answering wrongly, no issues about that. You just have to remember. You have to again, before your final exam, if you have to again go through the slides or uh, recording, you have to remember that, nothing else. So only the problems are conceptual questions. Okay. Now next MCQ is, which one of the following, this one will be the last MCQ as the time is over, so we'll end with this MCQ. So which one of the following IDF curve generation techniques is suitable to predict extreme values of rainfalls? Example, maximum rainfall. So option A is log normal distribution. Option B is Gumbel's extreme value distribution. Option C is log Pearson's type 3 distribution. And option D is sewage stormwater volumetric distribution. So what is the answer is basically, I am telling you the option B, Gumbel's extreme value distribution. Okay, so what is this IDF curve generation techniques? So this just again and memory based question. Okay, so we will actually just let me see one thing. Yeah. So this IDF curve generation technique, what is that? We'll see in the next class. Yeah. So in the next class there is another one. IDF curve is there. Yeah. So yes. So what we'll see one MCQ, how the IDF curve looks like in the next class. Or maybe one more MCQ should I discuss? Okay, leave it. We'll discuss in the next class. So if you have any question up to the last MCQ, you can ask. So this thing you just forget. So one IDF curve we will see in the next class how it looks like, and we'll solve a MCQ based on that. Then we will understand this MCQ So if you are having any question based on the last MCQ, up to this last MCQ, this one, or anything previous that you can ask, or anything before that you can ask. Otherwise, we'll end the session. Thank you, Shuleka, and we'll again, if you don't have any question, we'll again meet at 29th September Sunday at 7 p.m. Okay. I'll unshare my screen, and I'll those of you today we actually discussed a very interesting problem at the start. So most of you are not able to attend that. The recording will be uploaded, so there you can watch it. Okay, then goodbye, good night. I'll wait for 1 minute before I. Okay.
Good night, sir.
I'll wait for a few seconds before I end the session. If you are having any doubt, you can ask. Otherwise, yeah, no doubts. Okay, then I'll end the session. Good night. Oh, recording to